Nice to meet you, everyone. Today, I'm talking about the radioactive decaying rule from time-dependent quantum mechanics. This is for my teaching demonstration lecture. Let's remember the fundamental rule of radioactivity, that is, exponential decay rule. So this is the example of uranium-235 nucleus. This nucleus has the half-life of about 7 by 10 to 8 years. Within this half-life, the uranium-235 nuclei decay like this, that is 1 over 2 after one half-life, then 1 over 4 after 2 times of half-life. In terms of mathematical formulas, this radioactive decay rule can be represented as this. According to the experimental data accumulated until today, this exponential decay rule can be common rule for all the radioactive nuclei. Now our problem is to explain this exponential decay rule. So here this P of t means the probability of radioactive decay of each nucleus per time. And indeed, to explain this Pt, we should learn something from time-dependent quantum mechanics. The time-dependent quantum mechanics is represented by the Schrödinger equation if we consider the non-relativistic limit. On the other side, if we consider the relativistic case, this time-dependent equation 1 should be so-called the Dirac equation. Summarizing the introduction, our today's goal is to understand the link between the experimental exponential decay rule and the time-dependent quantum mechanical formalism. We assume the eigenstates of the Hamiltonian as this. Here, H can be whatever of the Schrödinger or Dirac Hamiltonian. Then E means the eigenenergy. And also, please notice that orthogonality is assumed. And by using these eigenstates as basis, an arbitrary state can be expanded like this. And here, mu of E are the expanding coefficients. Next, we consider the time evolution of this state psi 0 as the initial state. Now we have to work for a little bit long formalism. First, assuming psi 0 as the initial state, we consider the time evolution with this Hamiltonian. And the time evolution can be given at this equation 5. Here, the expectation value of Hamiltonian, which is indicated as E0, obviously conserves during the time evolution. That is given as equation 6. And note that for radioactive decays of nuclei, this expectation value E0 indeed corresponds to the mean Q value, or equivalently resonance energy carried out by the emitted particles. Next, it is convenient to define this survival coefficient beta t, and that is nothing but the overlap of the initial and current states, given as equation 7. And by using the assumption that the psi 0 and psi t are both expanded within the basis of the eigenstates, indeed beta t can be given as the Fourier transformation of the energy spectrum mu e. And also notice that beta at the t0 can be 1 consistently to the initial normalization. This statement, that is, the Fourier transformation of the energy spectrum gives the survival probability, is well known as the Kirchhoff-Fock theorem. For more details, please see this textbook by Kucklin and Dorr. Then, after learning the Kirchhoff-Fock theorem, one can show that experimental exponential decay rule is equivalent to the Bright-Wigner distribution of the energy spectrum. That is nothing but the energy spectrum mu e squared is assumed to have the Cauchy-Lorentz form whose center and full width at half maximums are given as E0 and gamma 0 respectively, and that is given as the equation 11 here. Or this is equivalent to that the initial state psi 0 can be expanded as the equation 12 here, and here the exponential of the IAE with the real parameters A of E are arbitrary phase factors. Then, survival coefficient corresponding to this equation 12 is now obtained from the residue at the pole at E0 minus I gamma 0 half, that is, following some calculations, beta t is finally concluded as this form in equation 17. Then, the survival probability yields the well-known exponential decay rule, that is nothing but the absolute square of this beta t, that is the decaying exponential function. And here, tau, that is h bar over gamma 0, is the lifetime of this metastable state. To conclude this equation 17, you need to perform a complex variable integration according to this counter. Actually, this is a good exercise after this lecture. Finally, we have shown that the Breit-Wigner energy spectrum indeed corresponds to the well-known exponential decay rule. So congratulations, we did our task today. After session. So today I have shown the simple example of the radioactive decaying rule by using some technique from time-dependent quantum mechanics. However, in practical applications, you may encounter more complicated problems. First of all, the model space needs a truncation by the energy cutoff, for example, from 0 to E cut, and this cutoff provides a deviation from the exponential decay rule. In other words, the problems in our real world cannot be represented as the exponential decay rule exactly, but there is always some errors. Second, it is necessary to discretize the continuum states like this psi t in terms of the discretized energy spectrum μn in numerical calculations. Also, the numerical solution of the eigenstates for basis needs another effort. Indeed, if the Hamiltonian is really complicated, to solve all the eigenstates for basis is practically demanding. I also recommend, before going to the metastable problem, it is better to check the accuracy of that solution method by doing some benchmark calculations. Finally, the way to fix the initial state, as well as its correspondence with the experimental situation, should be considered carefully. For example, the initial state of the multiparticle emission is usually characterized as a state where the emitted particles are localized in a narrow region and has the outgoing boundary condition. Even though these additional problems happen, however, I believe that the first step study we did today will be helpful for your future studies. Thank you very much for your attention today.